Every time a shaft turns, the balls inside the bearing carry the load. And the faster the shaft spins, the harder those balls are pushed outward by their own weight. Replace steel with silicon carbide and the ball weighs barely 40% as much, so the bearing can turn faster, run cooler, and last longer in service that would grind through a softer material. Silicon carbide sits at roughly Mohs 9 on the hardness scale. Only diamond is harder among common engineering materials. So the contact patch where the ball meets the race wears away far more slowly than steel against steel. The material shrugs off acids, alkalis, and most industrial solvents, so it keeps its surface in chemical environments that would pit chrome steel. And its thermal expansion, near 4 parts per million, is about a third of steel's, so the fit between ball and race barely shifts as the temperature climbs. At an elastic modulus near 410 gigapascals, the ball deforms less under the same contact load, which keeps the bearing geometry accurate and reduces the heat generated in the contact zone. As a bearing speeds up, each ball is pushed outward against the outer race by centrifugal force, and that force grows with both speed and mass. A silicon carbide ball sits at roughly 3.1 grams per cubic centimeter, about 40% the density of steel. So at the same speed it presses outward with less than half the centrifugal load. Less outward force means the ball can orbit faster before heat and stress reach the bearing's limit, so the same bearing geometry can turn at a higher speed with ceramic balls than with steel. The reason high-speed spindles and turbopumps specify them. The lighter ball also loads the race less at any given speed, which shrinks the contact patch, cuts the friction heat, and lets the bearing run at a lower temperature, extending both the lubricant life and the ball's own service. Standard bearing ball diameters typically start near 1 mm and step through common sizes 2, 3, 5, 8, 10, 15, 20, and 25, up to about 50 mm for heavier duty assemblies. The actual diameter is held to ISO 3290 precision grades, commonly G5, G10, or G25, depending on how tight the bearing's clearance must be. At the tighter grades, the ball's deviation from a perfect sphere drops to fractions of a micrometry, and the surface finish is polished to a mirror. Beyond the common sizes, diameters, grades, and surface finishes are matched to the bearing or seal assembly the ball will sit in, so a non-standard application still gets a ball ground to the geometry it needs. Each bearing type places a different demand on the ball. In a deep groove bearing, the ball carries mainly radial load, and what silicon carbide offers here over other ceramics is its chemical inertness. Acids, alkalis, and solvents that would pit silicon nitride or corrode zirconia leave the silicon carbide surface unchanged, so the bearing can sit submerged in a chemical pump without losing its race contact. In an angular contact bearing, the ball sees combined radial and axial load at high speed, and two features of silicon carbide matter most. Its elastic modulus near 410 gigapascals keeps the contact angle stable under load where a softer ceramic would deflect, and its thermal conductivity, around 120 watts per meter Kelvin, roughly 4 times that of silicon nitride, pulls friction heat away from the contact patch so the bearing stays cool at speed. In a thrust bearing, the load is purely axial and the ball is pressed flat between washers, so compressive strength rules. Silicon carbide's 3,900 megapascals gives it a wide margin. A self-aligning bearing tolerates shaft misalignment, and here the choice is more cautious. Silicon carbide's fracture toughness is lower than silicon nitride's, so tighter grade control and smoother surfaces are specified to keep contact stresses even. Where the entire assembly must resist corrosion, a full ceramic insert bearing in a chemical line. Silicon carbide's inertness across the full pH range is the reason it is chosen over every other ceramic. Consistently, each bearing type draws on a different edge of the same material, and the ball is specified to match. Grade, finish, and diameter tolerance all set by the duty the bearing must carry.